This lab is about discrete time Fourier transform. In the previous lab, we have studied continuous time Fourier transform. Actually, we are taking the transform of a signal. Signal can be a continuous time or can be a discrete time. If a signal is a continuous time, then it is known as CTFT or continuous time Fourier transform. Whereas if the signal is discrete in nature, in that case we will say it is discrete time Fourier transform. If we revise the concept of last lab, there we have a signal x of t and we can take its Fourier transform by taking integral of this signal and multiplying it with e minus j omega t. So x of omega will be is equal to integral from minus infinity to infinity x of t, which is our actual signal in time domain, multiplied by exponential minus j omega t and dt. So in this way we can transform a continuous time signal into frequency time signal. Similarly, if we have a signal which is discrete in nature, in that case the signal will be x of n. X of n represents that a signal is discrete, and we can take its Fourier transform by same method. The difference will be we replace this integral with summation sign and the range will be minus infinity to infinity. X of t will be replaced by x of n because now we are talking about discrete time signal, and exponential will be like minus j omega n. So this is the method which is used to convert a discrete time signal into its frequency domain. We can represent this signal x of omega in two different forms. The first one is rectangular form, and the second one is polar form. So this x of omega can be represented in two forms. In rectangular form, we will represent it like x of omega will be is equal to real part of this signal plus j imaginary part of this signal. Whereas in polar form, it will be represented in the form of its magnitude and phase. So the magnitude will be x of omega. This will be the magnitude, and its phase, or we can represent it with phi, will be argument of x of omega. So this signal, this discrete time signal in frequency domain can be represented in these two forms. In MATLAB, we have some built-in functions. By using those functions, we can calculate all the values of these different parameters. For example, if we talk about real part, or if we want to calculate the real part of a signal, we just need to write this signal in a built-in function of real x of omega. If we want to find imaginary part of a signal, we need to write imaginary x of omega. Similarly, this magnitude can be found by a built-in function of ABS, and this phase can be found by a built-in function of angle. As we have already discussed, this lab is about discrete time Fourier transform. So if we go through its manual, here we can see its equations. X of e j omega is equal to summation from minus infinity to infinity x of n e power minus j omega n, and we can represent it in two forms. The first one is rectangular form and the second one is polar form. And here you can see in rectangular form the signal in frequency domain is equal to real part of signal plus j imaginary part of signal, and in polar form we can represent it in two values in the form of its magnitude and in phase. Now we will code a simple signal to understand DTFT in MATLAB. If we go through a question, here write a MATLAB program that takes input the value r is equal to roll number over 100. So you can put your roll number in here and divided it by 100, and theta. Determine and draw plots of real and imaginary parts and magnitude and phase spectrum of the following DTFT. So a signal is given in frequency domain, as you can see, capital G e j omega. So the signal is in frequency domain and you are asked to plot its real and imaginary parts and its magnitude and phase. As we already know that in MATLAB there are 4 different built-in functions. By using those functions we can find all the values of these. So we will attempt it by putting the value of r, as r is equal to roll number divided by 100. So first of all I will assume roll number, let's say it's 40. Then r will be roll number divided by 100. After that we need to put the value of theta. As the value of theta is not given, so we can assume the value of theta in this case. Let's say theta is equal to pi, and we are assuming this value. Then we will write the equation of this signal, which is 1 over 1 minus 2r cos theta exponential power j omega plus r square e power minus j 2 omega. But before that we need to declare a symbolic variable of omega. So I will initialize the symbolic variable here and then start with the equation, which is 1 over 1 minus 2r 1 over 1 minus 2 multiplied by r, 2 multiplied by r, then multiply by cos theta. Cos of theta multiply by exponential power j omega, multiply by exponential power j multiply by omega plus r square exponential power minus j to omega. R square, I'll put it in the brackets, multiply by exponential power minus j multiply by 2 multiply by omega. So this is our equation. We need to find the real part of this signal and its imaginary part. To find the real part of this signal, we will use a built-in function of real. So in this way, we can find the real part of this signal. Now the next question is how to plot this signal. We can use the command of EasyPlot to plot the real part of this signal, but here we need to define the range of where its signal should be plotted. If we see the question, the range of r is given from 0 to 1, so we can define this range in MATLAB function. Range is from 0 to 1, and after running this program we can see the output of this signal. Similarly, we can plot the imaginary part of this signal, which will be, let's say its name is GIM for imaginary, and the function used imaginary of G. Then for magnitude, absolute function will be used, and for the phase, angle function will be used. As we have to plot 4 different values, so we can use the feature of subplot to plot all of these values in a single figure. Let's say we start with a subplot which has 2 rows, 2 columns and first box. You can see the output. In the first box of this, and I will write the same code for second box, but in this case I will plot the imaginary part. In the third box I will plot magnitude, and in the last box phase will be plotted. So these will be different responses. The first response shows the real part of the signal, second box shows the imaginary part of the signal, third box is magnitude, and fourth box is phase. Further, we can set titles for all these figures, so it will be easy to comprehend this figure. We can add legends, x-axis, y-axis, as we had already studied in the starting labs of SNS. Now we will go for the next question, in which it is asked to find the DTFT of a given signal. The signal is y of n. The signal value will be 1, where the range is from minus n to n. In the question statement you can see n is the roll number of the student, otherwise it will be 0. So first of all we need to define the value of n, and I am assuming the value of n is 50. It is basically the roll number of the student as mentioned in the question. So we need to find the DTFT of this signal. The range has been already defined. Now for where y of n is 1, range is from minus n to n. Let's say range will be n is equal to minus n to n, which will be minus 50 to 50 in this case. The next thing is, otherwise it will be 0. In this case we have already studied, to define it 1 we use the built-in function of ones in MATLAB. So in this way we can find the Fourier of this function, as we have defined the y, which will be ones of size of n. N is basically the limit given in the question statement 1, where n is from minus n to n, and we had already defined the value of n. We defined some symbolic variables here which will be used in this case. The Fourier command will be used to find the DTFT of this signal. And we had replaced the symbolic variable of t with the actual values of fn by using a substitute function of MATLAB. After finding the value of this signal in frequency domain, we can use these 4 built-in functions to find real part of a signal, imaginary part of a signal, absolute value, and phase of a signal. And then we can plot this signal by using subplot commands. When we will run this, we can see the output of this, where the real parts stand at 1, imaginary part is 0, as we can see no
complex number exist in this, and similarly magnitude and angle.